agriculture used in aquaculture. Man, while he domesticated many animals and plants, left the fish out. The carps and the trouts are relatively very recent attempts. The neglect of fish was perhaps mainly owed to man's unfamiliarity with the watery environment, and what is underwater is not seen as well. Man could commune with his terrestrial cohabitants and make them his pets and beasts of burden. He could watch his land livestock and easily recognize a sick cow or a chicken. Even when an attempt is made to learn how the fish performed, he could not comprehend it that easily. The major task for the aquaculturist is to breach this gap in knowledge and to know his animal before he really succeeds in rearing it to his advantage. He has to know the biological characteristics and potentials of the aquatic organism he wants to grow, and also the nature of its environment, that is, the physics, chemistry and biology of its ambient medium. Introduction. Culture fisheries are usually carried out in small water bodies which can be manipulated, pre-prepared for stocking, which are often manured and or fertilized before or during and after stocking, and or where fish are fed from extraneous sources. Pen culture, cage culture, culture in running water, in recirculating systems and in reconditioned waters are special types of aquaculture. All shades of intermediate stages between true capture and culture fisheries exist, such as in man-made lakes which are stocked extraneously, but where no manuring, fertilizing and feeding are generally done. Stocking is often done in large water bodies such as lagoons and rivers, where natural stocks have undergone depletion. The principles of management of capture and culture fisheries are very different from each other. In the case of capture fisheries, one has to attempt to harvest maximum sustainable yield by regulating fishing effort and mesh after taking into account parameters of population dynamics such as rates of recruitment, natural and fishing mortalities, fish growth and size at which recruitment occurs. Management of capture fisheries requires the knowledge of dynamics of the fish population under exploitation. In the case of culture fisheries, no detailed knowledge of the population dynamics of the cultivated finfish or shellfish is involved. Here one has to breed, if one technically can, the chosen fish under controlled conditions. If it does not breed naturally, and develop fish husbandry practices so as to be able to formulate economically viable technologies. For effective aquaculture, one has to gain familiarity and control water quality to enhance its biological productivity. One has to understand fish nutrition so as to be able to formulate nutritionally balanced fish diet. One has to delve deep into fish genetics so as to be able to evolve new varieties and strains which bestow commercial advantages to the product in terms of superior growth rate, nutritive value, bonelessness, taste, odor, etc. One has to prevent incidence of fish infections and diseases through prophylactics and therapeutics. Complete package of practices have been developed which involve accomplishment of several steps such as fish multiplication, nursing, tending and rearing of the young, all of which require special food for the larvae and the young fish. Then growing the young to marketable size, which requires special feed again and often intensive feeding for quick growth. The quality of the fish feed would naturally depend upon the species cultivated. Now we talk about different kinds of aquaculture. Notwithstanding differences in the physico-chemical characteristics of its habitats, viz. freshwater, brackish-water and seawater, aquaculture systems are of several kinds. Most of the systems are highly variable in magnitude and intensity, ranging to serve as one family units or large-scale commercial enterprises. The different kinds of aquaculture are static water ponds, running water culture, culture in recirculatory systems, in reconditioned water and in closed systems, culture in rice fields, aquaculture in raceways, cages, pens and enclosures, finfish culture cum livestock rearing, hanging on bottom and stick methods of oyster culture, Based on the number of species that are cultured in a system, aquaculture may be classified into monoculture and polyculture. Now we talk about ponds, pond culture, which is also called as static freshwater ponds. Ordinary freshwater fish culture ponds are still water ponds. They vary a great deal in water spread area and depth. Some are seasonal and some are perennial. The ponds may be rain-fed, also called sky ponds, and or may have inlet and outlet systems. The water supply may be from a stream or a canal or from an underground source such as wells, tube wells, etc. The water retention in the ponds depend on the soil composition of the pond bottom and subsoil water level. The natural biological productivity of such ponds depend on soil and water qualities. Homestead ponds are usually small and shallow. Commercial freshwater ponds have to have an assured water supply and inlet and drainage systems. In organized aquaculture, the carrying capacity of still water ponds is enhanced by manuring and or fertilizing and exercising water quality control. Fish are also fed from an extraneous source for obtaining fast growth. Science of freshwater pond fish culture has made great strides in recent years, and there is a fast advancing frontier of knowledge on every aspect of pond culture, starting from farm designing and construction up to the production of marketable fish, a wide variety of cultured freshwater species of finfish and shellfish. Examples are carp culture systems in India, China, Israel, Germany, etc., and catfish culture in USA. There is considerable competition with agriculture and other land use agencies in this system of aquaculture, and its success would by and large depend on comparative economics of land use. But much also depends on national policies on land use and the encouragement government gives to aquaculture as a means of producing fish protein. Now we talk about running water. Here brackish-water ponds are included. Not only are the species different from those cultured in freshwater ponds, but the principle of operation of brackish-water pond is different from those of freshwater ponds. Here the pond or the farm is essentially located on a tidal creek or a stream, and there is a system of sluices to control the ingress and egress of water into and from the ponds. Examples are milkfish farms in Philippines, Taiwan and Indonesia. Brackish-water fish farming is a fast growing science. Here also there is competition with other land use agencies, especially forestry, but the extent of competition with agriculture is relatively less because coastal land is generally not suitable for agriculture. The ARAC farm at Baguma is tidally fed and the salinity range is 5 to 21 parts per thousand. Mariculture. Mariculture is an aquaculture in the salt water of the sea. It may be in the seas, bays, etc. Example, traditional mariculture in inshore and offshore waters by a large number of countries, notably USA, France, Spain, Japan, etc. Mariculture of finfish in cages is relatively recent. Though a new development, it has assumed considerable importance and has great potential. Example, mariculture of several species of salmonids, namely Salmo salar, Oncorhynchus species of yellowtail, Seriola quineu radiata of red sea bream, Pagrus major, etc. Now we talk about running freshwater culture. In Japan, at places where there is abundant water supply, common carp is cultivated in running water ponds. The most intensive common carp is cultured in running water ponds. A very high common carp production rate of 980 tons per hectare has been achieved at the Tanka running water fish farm in Japan, where there is plentiful supply of running water of high dissolved oxygen content and optimum range of temperature for feeding. Running water culture of common carp is done in a small way in Europe, Indonesia and Thailand. We need to talk about recycled water or the culture in recirculatory systems. This system is comparable to running water culture systems, except that in the latter water goes waste, whereas here the same water is reused. In this system, water is filtered continuously and recirculated, often after aeration, to the fish pond. The filtering element is a biological filter comprising 3 to 4 cm diameter pebbles or honeycomb synthetic strips designed to arrest fecal matter and to denitrify catabolic wastes through bacterial action. The Motokawa fish farm in Japan is well known for carp production in recirculatory filtering ponds. This system has been tried experimentally for the carp fry rearing at the Central Inland Fisheries Research Institute, Barrackpore, West Bengal, India, with commendable results. A recirculatory system is sometimes classified as a system of wastewater aquaculture and reducing biological oxygen demand, that is BOD, of the wastewater. Several mechanisms of handling wastewater exist, viz. Pretreatment of wastewater, example cascading through a series of ponds, air systems, etc., dilution of wastewater, pretreatment and dilution, no treatment of wastewater. Restraints in wastewater fish culture systems lie in dissolved oxygen levels in ponds, toxic materials in wastewater, tastes and odor in fish. Parasites and diseases, public health problems, example Salmonella, Shigella or other enterobacteria, pond effluent standards and public acceptance. In reconditioned water, water reconditioning in aquaculture is necessary where there is inadequate water supply for the fish culture program or where water quality requirements are such that reconditioning is indicated. The different fish rearing systems using reconditioned water are simple flow through single pass systems, that is ample water supply of appropriate quality, that is from sources to fish rearing units to receiving. Single pass systems with pre and post treatment, that is from pre-treatment systems to fish rearing units to post treatment systems to receiving water supply. A system reusing water in fish rearing unit, example from pre-treatment system to rearing unit 1 to water conditioning treatment system for quality to rearing unit 2 and ultimately to post treatment system. The pre-treatment process used are sedimentation, screening, shocking to kill aquatic life, filtration, sterilization, aeration, degassing of nitrogen, carbon dioxide, etc., heating or cooling if necessary, and lastly pH control. The reconditioning processes are sedimentation, mechanical filtration, biological filtration, extended aeration, activated sludge, pH control, heating or cooling as the need be, sterilization, degassing and even ion exchange. Post treatment processes are aeration, sedimentation, filtration, disinfection, activated sludge, lagooning, digestion or equivalent, coagulation, absorption of taste or odor removal by activated carbon. These systems are mostly applicable to sophisticated and intense aquaculture. Here we need to talk about culture in rice fields, which is also called as pisciculture. Culturing fish and growing rice together in the same paddy fields is an old practice in Asia and the Far East. Interest in producing rice and fish together has declined in the recent years because of the use of fish toxic pesticides required to protect high yielding varieties of rice introduced as a part of Green Revolution in Asia. Now newer rice strains are being developed which inbreed resistance to insects and insect transmitted diseases which decrease the need for pesticide protection or growing rice. 4 trials conducted in Philippines on Tilapia mozambica and Cyprinus carpio stocking have resulted in standing crops of fish in paddy fields averaging 69 to 288 kilograms per hectare at harvest time. We now talk about cage culture and pen cultures, also called aquaculture in raceways using cages, pens and enclosures. Marine aquaculture farms may be located at 6 possible sites, viz. Either on the shore with pumped seawater supply, in the intertidal zone, in the sublittoral zone, or offshore with surface floating, midwater floating or seabed cages. The first 3 are enclosures and the last 3 include the cages. The enclosures in Europe have by and large stemmed from those set up for yellowtail farming in Japan, an example of intertidal enclosure. Edoic near Takasu in Inland Sea in Japan and Ardito in Great Britain. Since concrete seawalls or stone-pitched embankments are expensive, few intertidal enclosures are now built. Now we talk about the rigid structures. A large number of rigid net enclosures have been built in the inland sea in Japan in recent years, but not all are successful because of poor silting. It provides less circulation. Others are fouled by marine organisms which restrict circulation. More modern successful net enclosures have been positioned after hydrographic surveys to ensure sufficient water exchange and research on building material. Most suitable galvanized chain link and galvanized weld mesh, etc. Examples are Yellowtail, which produces 3.5 hectares farm at Sakaide in Seto Inland Sea, Japan. Fairy Isles, Lake Swin in Scotland. Bamboo barricades for milkfish farming in Laguna de Bay, Philippines. Sublittoral enclosures for salmon fishing in Norway. Sublittoral enclosure built in 1974 at Loch Moidart, 40 cubic meter capacity, tidal range of 5 meter. Now we need to talk about the flexible structures which involve buoyed fish net enclosure but resting on the bottom. Example, 10 hectare trial enclosure in Laguna de Bay, Philippines, and floating fish cages, a most important development of the decade in an aqua farming whose merits lie on their use where seabed is unsuitable for shellfish being off bottom. Predators can be controlled more easily and can be towed out of danger if threatened by pollution. Now we talk about cages with rigid framework. This includes 8 meter diameter and 6 meter deep ones having galvanized steel collar, galvanized chain link bag net for yellowtail farming in Japan, 14 meter diameter and 7 meter deep cages for salmon farming in Scotland and provided with rigid collars and catwalks for inspection of the fish, and 50 by 12 meter Pacific salmon cage at Reservation Bay near Anacortes, Washington, USA. Now we talk about cages with flexible framework, which include 55 meter diameter and 25 meter deep for chum salmon, that is Oncorhynchus keta in Lake Saroma at Hokkaido, Japan. Here netting material can be changed even when the fish are in stock. Midwater fish cage of the Haiketa Fishermen's Cooperative Association of Japan in Inland Sea, 9 meters by 8.25 meter deep with a buoyed feeding neck. These are grouped in 10 to 12 kgs which can be raised in the calm sea and lowered in the rough sea. Dome Sea Farm cage of Puget Sound, Washington, USA, which is 15.2 by 15.2 by 7.6 meters. Floating fish cage of Kampuchea and southern Vietnam are good examples. Let us discuss the merits of cage culture. Advanced type of aquaculture having scores of advantages over pond culture include 10 to 12 times higher yield than pond culture for comparable inputs and area, prevents loss of stock due to flooding, no question of seepage and evaporation losses, no need for water replacement, no problem of pond excavation and dependence on the soil characteristics, avoids proximity of agriculture areas, hence reduces the hazards of pesticide contamination, can be conveniently located near urban markets, avoiding the need for the fish preservation and transportation, eliminates competition with agriculture and other land uses, affords easy control of fish reproduction example in tilapia species. Complete harvest of fish is affected, optimum utilization of artificial food, reduced fish handling and initial investment is relatively small. Let us discuss the limitations of cage culture. However, they are difficult to apply when water is rough, high dependence on artificial feeding, high quality feed desirable especially in respect of protein, vitamins and minerals, feed losses are possible through the cage walls. At times interfaces with natural fish populations around the cage, and lastly, risk of the theft is increased. In view of all this, it is reasonable to consider cage culture practice as one which will prevail in future years. Research on this system deserves to be encouraged. Now let us talk about sea ranching and artificial recruitment. Here we need to talk on the hanging, on bottom and stick methods of oyster culture. In the hanging method, oyster as they grow are suspended from the raft, long lines or wrecks. Raft method is used in the protected areas as in the Seto Inland Sea of Japan. Now we talk about culture sites and its requirements. The culture sites are as per the requirements and generally located in the calm areas away from the hustle and bustle of the cities. Adequate water sources and agricultural or wastelands surroundings are more preferred. Here we need to talk about nursery and grow out ponds. Let us talk about the nursery ponds. The size of the nursery pond ranges from 500 to 2000 square meter with water depth of just 40 to 70 centimeters, that is, they are very shallow. Each nursery pond has at least one gate installed with a fine screen 1 mm mesh size to prevent the undesirable organisms from entering the pond as well as to prevent the escape of the stocks. Stocking density in nursery ponds is about 50 to 150 fry per cubic meter depending on the size of the fry. The nursery pond should be adequately prepared prior to stocking. Pond is completely drained of water and dried until the bottom soil cracks. Dairy's root at 4 gram per cubic meter will be applied when the pond cannot be completely drained. Lime at 500 to 2000 kg per hectare, chicken manure at 500 to 2000 kg and inorganic fertilizer at 25 to 100 kg per hectare are then applied. Recommended standards for commercial grow out ponds are: the pond leaves must be well compacted with a slope of at least 2:1. There should be no debris such as tree stumps within the pond leaves. Average water depth in a pond should be 1 meter, 0.8 meter at shallow end to 1.2 meters at the deep end. Inlet pipe at least 20 centimeter above the pond water level and screened with a properly fitted stock. Outlet pipe fitting with collar and screened correctly with a cone mesh. Freeboard of about 30 to 50 centimeter depending on the size of the pond and its leaves. Planted with grass are recommended. Having harvest basin is optimal but is highly recommended. Pond should be able to drain completely. The pond bottom should be firm without potholes and gently sloped 1 to 2% from the inlet to outlet. Preferably the pond should be rectangular in shape. Now we talk about the preparation, management and fertilization of grow out ponds. Pond preparation for stocking marks the beginning of the grow out production cycle before the pond is stocked for production. It should be prepared by removing excessive silt from the pond bottom. The bottom of the pond should be free of excessive amount of silt. It should also be dry and firm before filling. Silt removal should not be put at the top of the pond leaf as this will increase the freeboard, but rather away from the pond and or used to repair the pond leaf slopes. One should remember that much of the bottom silt comes from the slopes of the leaves. It should therefore be put back from where it came. If the soil is heaped on top of the dikes, it will wash back into the pond when it rains, because the bottom silt often contains high levels of nutrients. Example from the leftover feed, if the person is a bad feeder, and the feces, it is sometimes used to fertilize vegetable gardens. However, unless the feed input was excessive, the amount of nutrients in the silt is often not enough to justify the labor that is required to move the silt to a garden. When soil builds up on the bottom of the pond becomes shallower. Over time, the bottom mud becomes increasingly anoxic, that is without oxygen, forming hydrogen sulfide which lowers the water quality for production. This is a particular problem when a farmer overfeeds the fish, which can often occur when sinking feed is being used. After several seasons of mud buildup in the pond's yield and carrying capacity for the new cycle will therefore be lower than that of the previous cycles. If there is not much silt, the bottom can be left to dry until the surface cracks slightly before the pond is refilled with water for the next cycle. The cracks allow air to enter between the mud and aerate it. Alternately, the soil can be disked to aerate and increase the rate of decay of organic matter, which in turn reduces the rate of formation of substances such as hydrogen sulfide. Now we discuss the method of fertilizing the pond. There is no need to fertilize the ponds for catfish grow out if the fish are fed on nutritionally complete pellets. This is because all their food requirements are derived from the feed. Catfish grow out monoculture ponds feed nutritionally complete pellets only need to be limited if the pond soil is acidic, that is pH 5 and below. In this case, lime with agricultural lime preferably in the fine powder form by spreading uniformly over the pond bottom or the pond. The pond cannot drain completely. In this case, lime the remaining puddles with builder's lime, calcium hydroxide or quicklime until the water pH increases to 11. The objective of attaining such a high pH in this case is to kill off any fish, frogs, potential diseases or parasites that may remain within the pond. One should spread the lime over the pond bottom while paying extra attention to potential hiding places. This is necessary because any catfish left in a pond from a previous cycle can easily predate on all the new stock. After liming, the pond can be filled with water the following day, but only stock it when pH has decreased to below 8. Now we talk about the routine pond management. After initial stocking, routine checking of the pond conditions should be done every morning to monitor for physico-chemical parameters, physical conditions of the embankment, water supply and drainage canal and occurrence of undesirable species as well as the behavior of the cultured stocks. The early morning hours are critical for monitoring oxygen regime of the pond water. It is also important to inspect the feeding trays to verify that the feed given the previous day were consumed. If the feeds were not fully consumed, the possible explanation should be found and feeding rates adjusted accordingly. What is more important is water management. Frequent change of the pond water is needed to maintain the water quality. The process also helps to introduce new food organisms into the pond and stimulate molting of the shrimp. In stagnant water, decomposition of accumulated organic wastes or depletion of the trace metals may affect shrimp growth. The water in the pond can be changed through tidal flows or by means of a mechanical pump. Tidal exchange of pond water is normally practiced in traditional shrimp farm. Water in the pond is drained to 1/2 of the pond level during low tide and is replenished during the rising tide. The exchange is only effected within 5 to 7 days during the spring tide. Pond fertilization has to take place after the last day of the water exchange cycle. Now we talk about the stocking, feeding, monitoring and management. Recommendations for preparing ponds for stocking are: remove excess of pond bottom mud and dry the pond bottom. Ensure pond is not leaking and is deep enough. Undertake the necessary repairs. Screen the inlet and the outlet. Treat the bottom of the pond with lime if needed, such as if pond cannot drain completely. Ensure that there are no live fish left in the pond. Fill the pond. Maintain pond record sheets with the details of any management treatments. Check pond water quality before stocking. Many commercial hatcheries produce fish for sale to pond owners. It is best to consult several suppliers to see who has the best prices and delivery schedules. In most cases, the chemistry of the water of your fish are shipped in is very different from the water in your pond. When your fish arrive, adjust them to your pond water before releasing them or they may die. This is done by gradually mixing the pond water into the shipping container over the course of at least 30 minutes. Then lower the container into the water and let the fish freely swim out when they are ready. Do not pour the fish out. Now we talk about the monitoring and management. Regular sampling of shrimp stocks in pond is highly necessary to monitor their growth performance. This is especially important for adjust the amount of feed used according to shrimp size and standing crop. This is done through periodic sampling of the shrimp to determine their body weight. In the case of pinnate shrimps, seaning is not possible since these species are usually burrowing or wandering types. It is therefore difficult to obtain a representative sample. However, since these are hardy species, a cast net has been proven to be an excellent sampling gear. Usually 10 casts is sufficient to get a representative sample of 1 hectare pond. The dimension of a cast net should be measured to determine the area covered in order to calculate the total stock in the pond. Sampling in early hours of the morning or at night is preferable as the shrimps are more active during these periods and are more evenly distributed than during hot sunny day. For large ponds, 15 to 20 casts may be necessary to obtain a more accurate average. Now we talk about polyculture farm constructions. Monoculture, as the name implies, in the culture of a single species of an organism in a culture system of any intensity, be it in any type of water, freshwater, brackish or salt. Polyculture is the culture of several species in the same water body. The culture system generally depends on natural food of a water body, sometimes augmented artificially by fertilization and or by supplementary feeding. If artificial food is given, it is a common food acceptable to all or most species that are cultured. Example, freshwater polyculture of Clarias and tilapia in Africa, polyculture of several species of Chinese carps in China, Taiwan, etc., polyculture of several Indian major carp species in India, polyculture in Indian major carps, Chinese carps and other fish in India called composite fish culture in India. Brackish water examples are milkfish and shrimp culture in Philippines and Indonesia, mullet and shrimp culture in Israel. In systems where production depends on natural fish pond zonation, example ecological niches assume great importance. Records exist of the polyculture of various macrobrachium species in combination with single or multiple species of fish including tilapia, that is the common carp, Chinese carps, Indian carps, golden shiners, mullets, ornamental fish and red swamp crayfish. Other combinations may be feasible. The inclusion of the freshwater prawns in a polyculture system almost always has the synergistic benefit effects, which include more stable dissolved oxygen levels, the reduction of the predators, coprophagy, that is the consumption of the fish feces by the prawns, which increases the efficiency of the feed, greater total pond productivity of all species and the potential to increase the total value of the crop by the inclusion of a high value species. In addition of prawns to a fish polyculture system does not normally reduce the quantity of the fish produced. On the other hand, the addition of the fish to a prawn monoculture system markedly increased the total pond yield, but may reduce the amount of the prawns below that achievable through monoculture. Some problems have been reported. For example, tilapia, which was inadvertently introduced into the prawn ponds in Hawaii, were described as pests causing serious competition for food. Escaped tilapia, which had been grown in cages in freshwater prawn ponds in Puerto Rico, took years to eradicate. However, this problem could be avoided by the use of artificially incubated sex reversed caged tilapia. The monoculture versus polyculture decision is site specific and depends on economic factors, namely balancing the relative market values of the various species with the costs of the more complex management system. Fish are faster than prawns in assessing any supplemental food which is presented. So, the feeding for polyculture systems is normally directed at the fish and not at the prawns. The prawns consume feed which falls to the bottom of the pond as well as the fish feces and nutrients derived from detritus. Though commercial fish feeds are sometimes applied, tropical polyculture systems often use simple mixtures of rice bran with plant oil cakes such as mustard and the groundnut. And since there are so many potential combinations of fish and freshwater prawns, it is impossible to give firm guidelines on the management.
Now let us summarize field culture. It becomes obvious that the skills needed in aquaculture are multidisciplinary. Biology of the fish is the beginning. Biochemistry and water chemistry must be thoroughly known. The economic ways of constructing ponds and enclosures should be known. The need for fertilizers and the feed should be precisely understood. The growth processes as well as those of death causes and prevention should be known. Harvest methodologies and prevention and marketing needs and economics should be known too. Propagation of fish in captivity is an elementary necessity in aquaculture, for one cannot always obtain sufficient fish seeds from the wild to meet the demand. The whole process of breeding and nourishing fish according to the nutritional requirements should be known. To take a lesson from the well-trodden path of the agriculturist, the genetics of the fish for production of improved strains and hybrids should be known. Thank you.